Hey guys, today we are on lesson 0.2. We're going over functions, inverses, and graphing adjustments. So hopefully this seems a little familiar. So first let's go over some definitions. A relation. A relation is any set of order pairs, so x comma y. A function specifically is a type of relation. So for every x, there is only one y value. So for each x, there's one y value, okay? Which we found out earlier, a couple of years ago, that one of the ways to do this was using the vertical line test, right? Just kind of drawing a line all the way down, and if it crossed more than once, then you knew it wasn't a function, okay? And of course, we write our functions as f of x. Then we have the domain, which are all the x values that the graph goes through, and range are all the y values that the graph goes through. Okay, let me turn page. Okay. Let's go over some of these examples. Make sure we have this down. So we need to determine if each of these is a function of x. So one thing to keep in mind is that sometimes if we solve for y, we get our equation that will be easier to graph. So we know that this is a line, goes something like this. And of course, if we did that vertical line test, we only pass through the graph once. So yes, it is a function. Now the next one, luckily the graph is right there. And if we do our vertical line test, we go through it twice. So that is not a function. Now what I want you guys also to notice is the exponents, okay? So here, both of the exponents were 1, and it was yes. Both of them are 2, and it's not, so not a function. Here, well, let's keep in mind, what's an x squared, and what happens when it's negative and we add 1? That looks like this. So if we did the vertical line test, it works, right? We only go through it once, so yes. So let's go back and keep this in mind. This is x squared. X squared is here. So our problem was this y squared. Okay? When there's a y squared or y cubed, anything like that, we're running into issues. So here, this is x squared minus 1. If I were to solve for y, I would get y squared equals 1 minus x. To get rid of a square, we take the square root, but we have to remember the square root is plus or minus. So what this ends up looking like is something like this. Now, if we do the vertical line test, it happens that it is not a function. Okay. All right, number 5, we've seen this a lot, but for 5 through 7, we're evaluating. Evaluating is to substitute stuff in. So right here, if we have our f of x and our g of x, so I know I'm looking at the function of f. So instead of x, I'm going to highlight this, instead of x in that function, I'm going to put 10. So what that looks like is 3 times, now instead of x, we're going to do 10 minus 1. And then that gives us 29. Okay. 6, it's g, so we're going to use the g of x. And what we are substituting in for x is this x plus change of x. So all we're doing is substituting that in for every x. So it's going to be x plus delta x squared. Okay, we're just replacing this highlighted in this x. Now we can expand this if we want by squaring it, right? Don't forget, don't distribute the square, actually multiply it by itself. But it gets a little messy, so we're going to wait with that till later. Here, we're going to replace g of x, we're going to replace the x with the f of x function, okay? So g is x squared. So we're getting rid of the x and we're going to put f of x function in there. F of x function is 3x minus 1, and we are putting it into that square. Okay, again, we can multiply that out. So if you remember, this comes out to 9x squared minus 6x plus 1. Right? So this is, or you can have either one of these answers. All right, number 8, this is something you have not seen before. This is called a composition. So it depends on the order. So see how we saw this? It could be written like this, except that it would say G composed of F. Okay? So if I were to rewrite this one, we would say F of G of X. So for every X in F, we're going to replace it with the G of X function, which is X squared. So I look at my F of X, so I'm going to say 3. Now instead of X, remember I'm putting in the G of X, which is X squared minus 1. And that's composition. Okay, let's go over some domain and range. Okay. Now, lots of times the easier way to figure out domain and range is to graph it, right? Or we can think about our restrictions. So if you remember from last year, our restrictions were if anything was in the denominator, we had to make sure that it could not equal 0. And if anything was under an even root. Okay, so as you can see, we have a square root. So we know that under a square root, it has to be greater than or equal to 0. So when I solve, I get x is greater than or equal to 1. Now the great thing about this is that we can just keep that as x is greater than or equal to 1. So on the range, okay, what I would do is plug that value in. So 1 minus 1 is 0. So I know y is something to 0. And if I started plugging in numbers that are greater than 1, what happens to this? This keeps getting bigger and bigger and bigger. So that y has to be greater than or equal to 0. You could have saw that with the graph, right? Because it would have looked like this. And then we could have done domain and range also. Number 10, we know that what can't x be? X cannot be 2. Because if x were 2, you would have 0 in the denominator, and then we can't divide by 0. So that's your asymptote. Now, if we're talking about domain, we can either just say x cannot be 2, or we can write it in interval notation, which would be negative infinity to 2 and 2 to infinity. Okay, either way is fine. All right, so then we got to think that y then what happens with y? Well, y cannot be 0. And we know this because of the rational function. Remember, because at 2, we would have a vertical asymptote. And then what happens is our graph does our little curves, but it never crosses to the y-axis, or x-axis, sorry. Okay. Graphing. The graphing is so much easier, right, for domain. So we can either put it in as it goes from negative infinity to 0, 0 to 2, 2 to infinity. Or we could have just said the domain will not be 0 or 2, right? Because those are asymptotes right there. And then when we look at the range, we see that it goes from negative infinity to 0, right? Negative infinity to 0, but it doesn't reach 0, so it's a parenthesis. And then it starts right back up at 1 to infinity. Now at 1, it equals 1, so it's going to be a bracket. Okay. All right, 1 to 1. Some of you may have heard this, not everyone might have. 1 to 1 means that the function's inverse is also a function. Okay. So the way to do that is actually you could do the graph and do what's called a horizontal line test. So the horizontal line test, sorry guys, the horizontal line test is to see if the inverse is a function. Now, the inverse, if we were to solve for the inverse algebraically, we do that just by switching x and y and then solving. We need to remember, though, to change y to f to the negative 1 of x, okay? That is the inverse. So let's do some examples right down here, okay? All right, let me change colors. Which of the relations in 1 through 4 is a function with an inverse? So if I look back at 1 through 4, I already know which ones are functions. So the functions that I'm going to look at are 1 and 3. 1 and 3. I know it's not 1 to 1 for 2 or 4 because we already don't have functions. So on 1 and 3, I'm going to look for a horizontal line test. If it passes the horizontal line test, it is 1 to 1. So on this one, when they do the horizontal, the inverse is the function. So yes, for number 1. But if we look at 3, we run into where it hits it twice. So the only 1 to 1 function is going to be example 1. Here we go, right. Okay. And then in 13, we're going to solve for the inverse. So remember, the first step is to switch our x and y. And then we're going to solve. So x plus 1 equals 2y cubed. Okay, I'm going to put arrows so that way everybody knows where my work is. Then I'm going to divide by 2, so we get x plus 1 over 2 equals y cubed. To get rid of cube, we cube root it. X plus 1 over 2 equals. Now, instead of y, though, oh, and this is cube, so cube root. There we go. Instead of y, I'm going to put the inverse. And that is our answer. All right. Piecewise. Piecewise function, you're taking it in pieces. I am going to highlight some of these, but I don't know if I have another color here. Let's do that one. Okay. So what you see here, so it's pieces. You have to break it down. So we're able to graph the line X, right? It's just our diagonal line. But I only want that piece of graph to be between negative infinity and 0. And I need it to include 0, so it's going to be filled in. So that's where that comes in. Now, the second part is another linear one, but it's 2 minus x. So it goes in the opposite direction, and the y-intercept is at 2. We're going to do that from 0 to 1. The other way that you could graph this, guys, is to actually plug in 0. So 2 minus 0 is 2, and it's not equal to, so that is why it's open. And then we're going to go all the way to 1. It's linear, so I'm okay with just plugging in 1. 2 minus 1 is 1, so I'm only going to 1. Now that part would have been open, right? The only reason why this graph is closed right now is because it has to do with the last piece. The last piece is going to be a parabola, but the parabola is only going from 1 and greater. The best thing to do first is to plug in 1. 1 squared is 1, and that's equal to, so it's filled in. And then what you can do is just go, okay, what's 2? 2 squared is 4. 3 squared is 9. And then you know it curves up. Okay? So that is how we do pieces. Now let's try to do it ourselves, and then we're going to do our domain and range on this. So first of all, what I want you to look at, and I'm going to do this in colors, okay guys, I'll do green and pink. So this is an absolute value. If you remember, absolute value is a V, okay? But we're only going to do it from less than 1, and that is a hole right there, okay? So your regular absolute value has that V right here. So I'm going to start actually at this endpoint and go left. So 1, the absolute value of 1 is 1. Remember, it's open. And the rest of it on the left is the rest of the V. So we have this part here, and we have our V continued. Now, here is linear, right? X plus 2 is linear. So I know I'm going to start at 1, so I'm going to plug that in. 1 plus 2 is 3. So at 1, I'm at 3. It's filled in because it's equal to. And I know I'm going to go to the right because it's greater than 1. And the slope is 1. So I know that my line is this way. Again, if you have to and you don't think of it as slope, you can start putting in like, okay, 2 plus 2 is 4. So at 2 it's 4. 3 plus 2 is 5. So on and so forth. All right, zeros. When you are asked to find zeros, you want to say that y equals 0, okay? So when you write zeros, you don't need to write the order pair. You need to write it as x equals, okay? Now when you're doing x-intercepts, that's when you do the pair, okay? Intercepts are your pair, okay? So let's do some problems. First thing I'm going to do is take my function, set it equal to 0, and solve. Best thing to do right here, factor. If you have trouble factoring, we need to sit down one-on-one and learn those skills and really fix them, because you want to be able to factor it like that. So I know it's going to be x minus 4 times x plus 1. And so each of these parts, what makes that 0? What makes that 0? So that means x equals 4 and x equals -1. For 16, when we want to know what makes it 0, when we want to look at the zeros, we only look at the numerator. If you looked at the denominator, you're not finding zeros, you're finding the asymptotes. So we're going to look at the numerator. So we're just setting the numerator equal to 0. Okay, so just remember 0 over any number equals 0. So that's why. Okay, so x squared minus 4 is a special case. Remember, it's the difference of two squares. So we have x minus 2 times x plus 2 equals 0. So x equals plus or minus 2. The other thing we could do if you didn't want to factor, guys, is that you could have solved it as I'm going to add 4 to both sides and then take the square root. Next page are your notes. You're going to just want to skim this over and over or refer back to it, okay, guys? So I'm going to try to refer back to it while we're doing our practice problems. So here are your parent graphs. You need to memorize these so you get the idea, okay, that's what it looks like, okay? So you have your line, your parabola, your x cubed, your x squared, or no, that's x to the 4th because they're both technically parabolas, your square root, your cubed root, your 2 over 3, and absolute value, rational squared, and your circle, okay? These are the basic graphs you need to remember. This is the hard part. Let's remember that a negative out front makes it flip over the x-axis. X inside makes it flip over the y-axis. Adding on the outside makes it go up or down. Adding on the inside goes left or right, but it's the opposite. So I'm going to put that down so we don't forget opposite. Okay, the A out front does a vertical stretch or a vertical squeeze. The B or the inside multiplied by X does a horizontal stretch or squeeze. Absolute value, these are the ones that are totally new to us. So you want to make sure that you're getting these down because it makes it graph easier, okay? No graphing calculator, only checking on the graphing calculator. So if the whole function is in the absolute value, then what happens is you reflect all the points below the x-axis. So reflect all points below the x-axis, below the x's across, so below it. So for all of them below, and leave points above the x-axis alone. We'll show you that in a minute. And then if the absolute value, oh, here we go, alone. Eliminate completely all points on the left side of the y-axis. So completely, okay. Leave all points. I feel, guys, that we are a little off in the typing of it. So, yes. Okay, that's why. This one goes here. This one goes here. Sorry, it was the whole not capitalized middle of a sentence. So when the absolute value is on the inside, we eliminate the complete left side and then we reflect it over the y-axis. We're going to practice this so it totally makes sense. Okay, so first of all, I am going to show you that when you have a random function like this is the f of x function, it is easier to pick coordinates that you are going to move and then draw everything else in, okay? So if you see, we are adding on the inside, which means left or right, but since we're adding, we're going to the left because we have to think of it as opposite inside, right? So we're going left 2. So I'm going to take each of these points where they are and go to the left 2. And I'm going to be off the page a little bit here. I'm going to see this point that goes right here, and I'm going to go left 2. Go left 2. So there's that parabola part. Here's the original point. Go left 2. And there is my graph. Okay. Shifted it 2. Okay, now we have 2 movements here. The first thing we're going to do is flip it over. So reflect over x-axis. And then we're going to move up 2. All right, I'm actually going to not do my marker in this end. Excuse me, guys. I'm actually going to do the first transformation and then do the second. So I'm going to do the first one in the purple and the second one in the green. So the first one's a reflection. So that point is 2 away. And it's going to be down here 2 away. That one reflects onto itself. And that one reflects down to here. And this one, which was right here, reflects up here. Okay, so this is the reflection transformation. That's just this part. So if we were to do all of it, now I need to move each of these points up 2. So 1, 2. 1, 2. 1, 2. 1, 2. On a test, guys, when you have to do this, if you have multiple transformations and you want to do them separately like this, all I need you to do is tell me that the green or whatever color you choose is your last transformation. And that's your final. Okay, that way you don't have to erase and do everything like that. All right, let's talk about what's happening here. So when you do multiple transformations, the first thing to do is the inside, and then when you do the outside, go left to right, like you read. So the first thing this tells me to do is reflect over y-axis. It's y-axis because this is negative x inside. And then we're going to squeeze vertically. I can't spell. Vertically by half. Now, it is on the outside, so we do exactly what it says. Okay? It will change a little bit here, and I'll explain that in a minute. Okay? So let's do the first one. Let's flip it over the y-axis. So it would have been here, so we're going to go 2 across. That is at a 1, so we're going to go 1. That one stays the same. And instead of it being over here, we are going over, that's going to be 3 right here. Okay, so this is flipping over the y axis. So that's the first thing. Now, the second thing, which I will do my final answer in green again, I'm going to multiply all the y values because it's vertical. If it's vertical, that means we multiply y values. These are little notes that you want to make sure that you keep studying, because these are new things that we didn't push you to do in secondary math. So I'm going to take all the y values. So this y value is at, sorry, lunch or B lunch is starting. So this y value is -1, so cut that in half, you get -1/2. Okay, this y value is 2, cut that in half, we get 1. 0 cut in half is 0, and then 2 cut in half is 1. So again, my green is the final. Okay. Crazy. Okay, next. Remember, last time I said do inside first and then outside. So what do we see on the inside? We see 2 times x. Well, what that means is there is a horizontal squeeze Okay, now remember how on the inside moving left and right was opposite of what you thought? It is the same thing when it comes to multiply, but don't think of opposite like, well, I guess you can say opposite is the opposite of multiplying is dividing. So dividing by 2 is the same thing as multiplying by 1/2. So do the reciprocal. Okay, so when it's on the inside, you multiply by the reciprocal. And then after that, we're going to take that absolute value on the outside. Absolute value on the outside says reflect points that are below x-axis above. So we're going to take everything below the x-axis and flip it up. Okay? So let's do that horizontal squeeze first. So we're multiplying, and by the way, it's on the inside, right? So we're multiplying the x values because it's a horizontal squeeze. X values. This is new, so it's going to be harder to remember. So the more you study, even if it's with note cards, the better. All right, so if the original was here at -2, and I multiply the x value in half, that means I get -1 for the x value. At 0, 1, and I multiply the, or -1, 0, sorry, -1, 0, and I multiply that in half, I get -1/2. The other one was 0, 2. Well, if I multiply the x value, which is 0, by half, I still get 0. And then right here, if I multiply the 3 by half, I get 1/2. So I'm right down here. Oh, and I should have done that in purple, right, guys, if I want to be consistent. Okay. So what happens there? Well, now we have to reflect the points below, okay? So look at what's below the x-axis. Below the x-axis is right here. So what we're actually going to do now to finalize it is flip that yellow piece up. Okay, so the final transformation is right there. So you flip that piece out. Now let's practice absolute value on the inside. Absolute value on the inside says eliminate all points left of y-axis then reflect across y-axis. Okay, so if I look at the original here, I'm getting rid of all of this, right? So if I eliminate the left side, all I am left with is this linear equation, right? That's what I have. Now, the second part, though, was to reflect what you see over the y-axis. So luckily, this is on itself, so it stays there. But if I reflect, I end up over here, and it becomes this V. Again, more practice you do, the better, easier it will be to remember all of these transformations. All right, you are ready to do your practice work. See you guys later.